Hello, good day all. On behalf of all the co-authors of this paper, I'm here before you to present this paper titled Buck-Boost Converter with No Dead or Overlap Time. Happy listening. Thank you. Buck-Boost converters, BBCs, are DC-DC converters capable of stepping up or down their input voltages Vs to a given output voltage V0, as shown by the relationship in equation 1. Diodes of BBCs are replaced with synchronous MOSFETs to reduce conduction loss. This requires overlap time to avoid all the switches from being off. Impedance source converters, ISCs or ZSCs, permit shoot-through and open circuit. Shoot-through, this refers to the phenomenon that occurs when all the switches of the same leg of a bridge circuit are on. Open circuit, this refers to when both the switches of the same leg of a bridge are off. This is prohibited in both the 2-switch and the 4-switch BBC. Impedance source converters allow terminal current interruption of a current-fed impedance source converter without causing overvoltage oscillation for current boosting. Reference 3 proposed a modified impedance source converter called quasi-Z source converter by swapping the position of switches and inductors in the classical Z source converter. Reference 4 extended quasi-Z source converter application to DC-DC with gains given by equation 2 and equation 3 below. Common deficiencies of simple impedance source converters include lower gain at a given duty ratio during boost mode, or discontinuous gain as compared with the traditional buck-boost converter. Proposed topology. This paper proposes a buck-boost converter using a quasi-Z source converter topology, thus eliminating dead and overlap time requirements. Features of the proposed topology include: the gain of the proposed topology is similar to the gain of the classical buck-boost converter. Thus, the gain is larger than that of the quasi-Z source converter given by equation 2 and continuous when compared with the gain of the quasi-Z source converter given by equation 3. Its properties such as impedance network, 2 capacitors, 2 switches, and 2 inductors, shoot-through permissibility, etc. are those of a quasi-Z source converter. This proposed topology may be referred to as buck-boost quasi-Z source converter due to its shared properties of the buck-boost converter and the quasi-Z source converter. Verification. To verify the operation of this proposed converter, its operation for 2 different modes, buck and boost, are compared. The topology of the proposed converter. This is the topology of the proposed converter. As discussed earlier, it has 2 inductors, that is L1 and L2, 2 capacitors, C1 and C2, 2 switches, S1 and S2, then a single input voltage source, Vs. The output R0 is taken across the capacitor C2. Circuit analysis. Here, the circuit analysis of the proposed converter is presented. This is to derive the gain equation of the proposed converter. The converter is operated using two switching modes, that is mode 1 and mode 2. Mode 1. During this mode, S1 is switched off while S2 is switched on, as shown in figure 2a. During this mode 1, two equations are derived, that is equation 3 and equation 4. Equation 3 is derived by applying Kirchhoff's voltage law in the loop A, B, C, A, and simplified as VL1 equal to V0 minus VC1. The second equation, that is equation 4, is obtained by applying KVL in the loop B, C, D, B, that is VL2 equal to Vs. Mode 2. During mode 2, the switch S1 is turned on while S2 is turned off, as shown in figure 2b. Also, during this mode 2, two equations are obtained, that is equation 5 and equation 6. Equation 5 is obtained by applying KVL in the loop A, B, D, A, and simplified as VL1 equal to Vs minus Vc1. The second equation, that is equation 6, is obtained by applying KVL in the loop A, C, D, A. To obtain the gain of the proposed converter, volt-second balance is applied on the inductor L2 during a complete switching period. This simplification leads to having the equation 7, that is VL2 equal to dVs plus V0 into 1 minus d equal to 0. Further simplification of equation 7 results in having equation 8, that is the gain A equal to minus d all over d prime. Equation 8 is the ideal gain of the proposed converter. So equation 8 is the same as the gain of the buck-boost converter given by equation 1 earlier presented. This shows that the buck-boost converter can be obtained using this quasi-Z source converter topology. An advantage of the buck-boost converter over the quasi-Z source converter with gain of equation 2 is that for a given duty ratio, it has a higher gain than the corresponding quasi-Z source converter as shown in figure 3. The quasi-Z source converter with gain in equation 2 has discontinuous. So this is the comparison of the two gains, that is the gain of the quasi-Z source converter and the gain of the buck-boost quasi-Z source converter. Experimental verification. A hardware prototype of the proposed converter was fabricated and tested with gate signals without dead or overlap time. Atmel AT-SAM3X8 microcontroller was used to generate two complementary pulse width modulation signals with no dead or overlap time. The complementary PWMs were connected to the converter via two gate drivers. Values of the parameters used for the verification are shown in Table 1. Parameter values used for the prototype development. Vs equal to 3.5 volts, duty ratio during bulk mode over 0.35, boost mode duty ratio over 0.65, switching frequency of 50 kHz, C1 and C2 values of 0.9 and 0.01 microfarads respectively, L1 and L2 values of 33 and 470 microhenry. Load resistance of 150 ohms was used for the verification. The experimental setup is shown here in Figure 4A and Figure 4B. Results. Here, results of the experimental verifications are presented. Figure 5A shows the PWM signal used to switch the gates of the MOSFETs. As shown, the PWM signals have no dead or overlap time. In Figure 5B, the response of the proposed converter during buck mode is presented. The figure has three waveforms. Top is the input current waveform, middle is the output current waveform, then bottom is the output voltage waveform. Figure 5C shows the response of the proposed converter during boost mode, also consisting of three waveforms. Top is the input current, middle is the output current, and bottom is the output voltage waveform. Discussion. The waveforms of Figure 5 confirm the operability of the proposed buck boost converter. As shown in Table 3, the values of the proposed converter's operation during buck mode and boost mode are shown. These values were obtained using a digital multimeter. The value is compared with the ideal theoretical values. The experimental results were less than the ideal voltages due to parasitic voltage drops by the reactive components and the switches. The input and output current waveforms have ripples due to transients that occur during switching, and also because design equations were not used to develop the prototype. Conclusion. Operation of a buck boost converter without dead or overlap time delay is presented. Its operation for buck and boost modes were also presented to confirm the operation of the converter. The advantage of the proposed converter over traditional buck boost converter include permissibility of higher frequency operation due to the elimination of overlap time. This implies saving cost and weight because smaller components could be used due to higher frequency permissibility. Listed here are some few references for further reading. Thank you. For further information or inquiries, suggestions, you can please send us your feedback. Thank you.